So yeah. So let's just start. So what we're going to do today, we're going to talk about some more theoretical things. The first, I'll briefly discuss the existence and uniqueness of a solution of the following stochastic differential equation of a particular form. So let's just quickly go through proof of it. So what is the stochastic differential equation? So the stochastic differential equation is really the standard. So it's a stochastic process that's an Ito process. In other words, that it's a stochastic differential equation of this form, at dt plus dt x of t dwt, where x of 0 is x naught, okay, and the t is anything from 0 to what do you call it, capital interval t. So you have a generic stochastic differential equation, could be linear, could be non-linear. A's and B's are non-linear, then there's a non-linear stochastic differential equation. And the question is that, under what conditions there exists a unique solution of this stochastic differential equation. So in other words, the question is the question of the well-posedness, actually, that under what conditions solution exists. So here's the theorem. So I wrote it last time, so just quickly write it. So suppose that these functions a and b are Lipschitz. They are Lipschitz in second component. Okay, in other words, in second components they are Lipschitz, and
what does it mean? Second component means x of t.
in other words, if you a comma b, in other words, if you look at this function a as t with something here, then this is a second component actually. Okay. So in other words, what does this mean? That if you take a t of say x and a t of y, okay, you can estimate this by, in other words, there exists a constant k positive such that this is satisfies this kind of a condition actually. Okay. So with respect to the second component, it's Lipschitz, and with respect to the first component, in other words, with respect to space hysteresis and with respect to time, it's uniformly continuous actually. And uniformly continuous with respect to first component. And remember the definition of uniform continuity. So it says that for all epsilon positive, you can find a delta positive, but that delta only depends on the epsilon. Okay? Such that if you take any two instants, say t and s, okay, which are at distance delta, then this implies that the ut x minus atx minus as x is less than epsilon. It's really what do you call the uniform continuity. Okay. Alright, so it's Lipschitz with respect to second component and uniformly continuous with respect to the first component. Okay. And the both function have linear growth actually. Okay. And both have linear growth. That is, moreover, there exists a constant k positive, okay, such that such that for all t in the interval 0 to capital T and x, y, in R, this condition is true. In other words, that a tx minus a ty plus b tx minus b ty is less than or equal to k times of 1 plus absolute of this k times x minus y. Okay, so this condition is satisfied. So you can find such a k because a and b both are Lipschitz. Okay, so since a is Lipschitz, so this expression would be less than or equal to some k times x minus y, and since b is Lipschitz, so this expression would be less than or equal to some k times x minus y. So if you take the maximum of both k's, you can have this expression actually. So such kind of a k exists. And a and b has linear growth actually. So in other words, if you compute, for example, the values of a and tx and compute the value of b times tx, it could be less than or equal to some constant times 1 plus absolute of x actually. Okay. This is for all x in R and for all t in the interval 0 to t. So this property is called that a and b has a linear growth. Okay, has a linear growth. In other words, this is dominated by a linear function, and b is also dominated by what you call a linear function. Okay. So if you have a and b which are Lipschitz and uniformly continuous in time and have linear growth, so if you have such kind of k's and b's, then there exists a unique solution to this star. Is it making sense? I'll just give you maybe the sketch of it and you can read it for yourself. Maybe I can go in, for example, one of the proof in detail, and then maybe you can do the rest for yourself. So if A and B satisfies this, then you are okay, you can always find it. So what would be my argument? So what is the proof? Proof is this. So what is the So when I'm saying that I have an x that satisfies this stochastic differential equation, we know that this stochastic differential equation is basically a cryptic way to write an integral equation actually. So in other words, a solution of a star, so solution of a star must satisfy. So otherwise you're going to say that a process xt is solution of a star if it satisfies this actually. So the x of t is equal to integral x naught plus integral in the diagram a sx ds plus 0 dbsx dws. Okay, so if satisfies this stochastic differential equation, then you're going to say that your problem has a unique solution. Okay. And what is the trick? The trick is to run what you call a fixed point argument actually. Okay. And in order to run the fixed point argument, what I'm going to do is that I'm going to call this right hand side, okay, a map actually. Okay. So I'm going to call this as what do you call some phi of x. And then by saying that I need an x that satisfies this stochastic differential equation, what we are actually saying that you try to find the fixed point of the phi actually. So that the phi of x gives you x. So if the phi of x is x, then that x would satisfy the stochastic differential equation. Okay? So let me write it precisely. Okay, it's not that really that easy. So you will ask, okay, if the solution exists, what basic properties that solution must have, and in what space the solution exists actually. So the solution space is this actually. So, and this is what happens when you, for example, trying to solve the abstract equations actually. Okay, you need to define the solution space. You need to tell that, okay, the solution exists, but solution, lives in what space actually. Because think about it, if you want to apply the fixed point theorem, you need to have a Banach space actually. Okay? You need to have a Banach space because you need to have phi as a map between two Banach space, and then you need to show that it's a contraction, and that will give you what do you call a unique solution. So the Banach space that I'm considering, or the space that I'm considering, is this ZT. So the ZT is what? It's a collection of the processes which satisfy this crucial condition that this x is adapted, first of all, and it satisfies this condition that expectation of 0 to capital T x square of t dt is finite. Okay? Or you can also write this condition as this actually. So in other words, it's really the crucial condition to be in L2AD. So I need so ZT is what? The space of all processes which are adapted and are in L2AD actually. So this is really the condition of being in L2AD.
Are adapted in what filtration?
Surely.
Filtration.
Everywhere generated by, so the filtration is the same filtration to which, with respect to which Brownian motion, Brownian motion is adapted to it, and it has independent increments actually. Okay, for simplicity you can take, for example, the natural filtration of the Brownian motion actually. Okay? Is it making sense? So this is what it really is. So for example, if you see from the Kapensky book, it puts the expectation here. It doesn't matter, but you can apply Fubini and have it. Okay? And on this space, here is a norm. So what do you think, what should be the norm on X? So this should be the norm actually.
So this is only JNX.
Okay? So the norm of this square is really the expectation of this 0 to t x square of t and dt actually. So this is the norm on it. Okay? Then what we can show that this ZT is a closed subspace. So it's a closed subspace of L2 omega cross 0 to t or 0 to t cross omega. Okay, so we know it's a. So this is what? This is the collection of all processes whose second order expectation, expectation of x square is finite actually. So we can show that this is a closed subspace of it. And we know, and this is a Banach space as well. And we know that if you have a closed subspace of a Banach space, it must be a Banach space itself actually. Okay, so the ZT is Banach space. I'm not getting into it that why it's closed. You can really prove it actually using the functionality argument. Okay, so this ZT xt is a Banach space. Okay, further details you can see from the book. I'll just run through the argument actually. Okay. Banach space, but you can say it's a Hilbert space. This guy is a Hilbert space. So it's going to inherit then a product from it. Okay. Is the required space. Okay. Call it a Banach, call it a Okay, so you have. So what is the proof? So here is the real, what do you call, steps of the proof. So the proof goes in 6 steps mainly. So the first thing is going to be that this map phi is a map from ZT into ZT. Okay, is well defined actually. Okay, it's well defined. And what is map phi? So the phi of x is this x naught plus this integral 0 to t and a of sx ds plus 0 to t and bsx and
DWS.
so that's my definition of phi of x. Okay, so first thing is that this is well defined map. And the second thing is going to be, the step 2 is going to be to show that this phi is a contraction actually. Okay? Phi is contraction on ZT1, where T1 is a sufficiently, small value actually. Okay? So T1
Subinterval is 0 to P.
is subinterval. So T1 is a small number depending on data. We'll talk about it, that how can I choose this T1 actually. Okay? So in other words, the phi is going to be Lipschitz, but it's not going to be in general contraction. So you need to shrink this interval 0 to t actually. So it's not contraction globally on 0 to capital T. We're going to show that it's a contraction on small 0 to t actually, T1, okay, interval. So this will be the second step. The step 3, okay, is going to be to show that this sequence, where x1 of t is x naught and xn plus 1 of t is phi of xn of t is convergent. Okay, so this is convergent in ZT1. Okay, so this is convergent in ZT1. The fourth step is going to be that this solution that we have on the interval 0 to t1, I can extend it onto another interval of the length, the same length actually. So t1 to 2t1. T1 to some, 2t1 actually, or t1 to some other t2, and then t2 to some other t3. And then, so in other words, so I have this interval 0 to t, so first I will construct an solution here in 3 steps. And then, so here I have initial condition x naught actually. Okay? So initial condition is x naught here. And I'll solve a problem with respect to this condition x naught. Okay? And then I find a solution that is valid from x naught to this t1 actually. 0 to t1. And then I'll say that now I want to solve the same SDE, but by taking the initial condition x of t1. Okay, and repeating the same procedure, so I'm going to get another solution that is going to be valid from t1 to t2 actually. Okay, it's going to be valid. So it's going to be a solution x that is going to give me at t1 this x of t1.
T1 to t2 or 0 to t2?
The 0 to t2 actually, t1 to t2. Okay, but I can put them together and I can have a solution of this. And similarly, I'll keep on constructing the solution unless I have a solution on this subinterval. And then I will say that yes, I have a solution for this entire time that behaves like this solution in this interval and behaves like this solution in this interval and behaves like the solution in this interval. So in other words, you just extend this actually. So whose restriction is a solution in each of the term actually. and that is going to the solution over the entire interval.
So solution limit होगी ना इस sequence की.
किसकी?
Solution जो होगा.
Piecewise होती है.
Limit of this.
It would be a kind of a piecewise function. We will get into it, we will see that what we are doing. So we are extending the solution up to the entire. So the next thing would be the extension of the solution. Extension of solution on 0 to t. And the final step is going to be, maybe the step 5. Okay. So step 4, okay, so this is going to be step 5. The step 4 is going to be that this solution that you have obtained in Z3, in other words, this x of t in ZT1 is unique actually. So in other words, on each subinterval the solution that we are getting is unique. And then we will extend the solution. And then the final thing is going to be to prove that our extended solution is unique. Okay, so we'll prove the uniqueness for extended solution actually. Okay. So the uniqueness of extended solution actually. So why I am getting into this proof for the first time actually? It's because that whenever you see a huge literature, okay, in which you solve different kind of SDEs with the different noises, here you have a Brownian motion, you can have a fractional Brownian motion, a G Brownian motion, or maybe a Levy process, or maybe some other kind of processes, and you want to show that for a similar kind of SDE the solution is unique. The argument is going to be almost on the same lines actually. Okay? Even a similar kind of argument you can use when you want to solve, for example, SPDs actually. So you have a stochastic heat equation actually. So you take the heat equation and add noise into it. Then you say that does this equation has a solution? Okay, so under some conditions, it's going to have a solution actually. And how you're going to prove that, for example, existence and uniqueness of the solution almost on the same lines. Okay, the tiny details are going to be obviously different. The spaces are going to be different depending on that what kind of equation you have. But argument is essentially going to be same. Maybe some different kind of fixed point theorem is being used, but you will have similar kind of an argument. Okay, so I'm just going through at least one proof so that you can have a picture in your head. So I'll be quick in doing each step. I'm not going to spend too much time on it. It's really a function analytic argument. Okay, so let's start with the step 1. So for step 1 you need to prove that this map is well defined actually. So what do you mean by the map is well defined? By saying that the map is well defined, you need to have that this map is a function actually. Okay? In other words, you need to show that if you take, for example, an x from zt, the phi of x indeed is an element here. Okay? So you need to show that phi of xt. So in other words, to show that the map is well defined, the crucial thing is going to be to show that phi of x belongs to what is called zt actually. And for showing it, what you need to do, you need to compute the adoptedness is not a big deal.
Okay, sir.
Okay, the real thing is going to be to show
Integral of that
integral of it. Okay, the integral of it. Okay, you can think carefully about the adoptedness as well, because think about it. We know the adoptedness of the stochastic integral. Okay, so if the process is adopted, then the stochastic integral is adopted actually. Okay, and you are adding something deterministic into it, so adoptedness is not a big deal. Okay, the real thing is to really compute this. So let's compute phi of x of t square. Okay, so it's going to be, so this x naught plus, 0 to t a. Okay, so a of s ds, I'm just quickly writing it, 0 to t of f, and it also depends on x of s, okay, for sure, dw of s and this square. Okay. Then I'm using an identity that if I have a plus b plus c square, this is less than 3a square plus 3b square plus 3 square. Okay? So this could be estimated by 3x naught square plus 3 times of 0 to t a of s ds square plus 0 to t d of s and dw of s square. Okay? Obviously you're going to have a 3 here as well. And then integrate it. Okay? So integrate it, that's what you need to do.
Yes.
Okay? Or you need to take the expectation and then integrate.
Both are same.
That could be another way to do it, that okay, you take the expectation, so this is going to be the expectation of it, and you have it. Okay? And then integrate it. So when you have to integrate, you have to just think of, let's think of every term actually, okay? So let's integrate from 0 to t, so this guy 3 times of expectation of x naught square. Okay? And say ds actually dt. Okay? But x naught is by definition, okay, so maybe I didn't mention it, but in our assumption, we have an assumption that x naught satisfies this condition actually. Okay? So it satisfies this condition. So x naught square expectation is finite. So if this is finite, so that's a finite number, then this integral is finite as well. Really what you need to show that if you integrate from 0 to t dt, this guy is finite. That's what you need actually. So you need to show that if you integrate each of the term here, and if all 3 terms are finite, then their sum is finite and hence this is finite. So the first term is finite. Let's think about the second term. Okay, this second term. What is second term actually? So this 0 to t a of s ds squared, okay, and its expectation and the integral 0 to t. Okay, so forget about 3 actually. Okay. So what I'm going to do, on this integral, inner integral, I'm going to apply, what do you call, Cauchy-Schwarz actually. Okay, so I would like to apply Cauchy-Schwarz on it. So in other words, so I can estimate this by 0 to t expectation of, so this is like my f and G is 1 actually. Okay, so this is going to be, what you're going to get. So you're going to have, okay, so one integral is going to be 0 to small t, okay, so a square of s, xs and ds, okay, and it's 1/2, right? 1/2 होगा
जी सर बाकी 1 करके
मगर अगर स्क्वायर है तो फिर ये 1/2 नहीं होगा, so not gonna have a 1/2 ठीक है, times 1 का integral
t होगा,
so it's gonna be t, so I can estimate even that t by capital T.
हाँ सही.
Okay, so this is going to be the case. Okay, and now what are you going to have? Do we know something about this guy? So we have assumption that this has a linear growth actually. Okay, so I can estimate this by 0 to t, expectation of okay, integral from 0 to t, so it's going to be constant times
1 plus
1 plus absolute of x square, okay, where x is x of s and ds